So we are going to discuss about sequences. So consider the following sequence. So 1, 3, 8, 9, 12. Question, what is the 100th term of this sequence? This was a Mensa puzzle. You can look at it. However, what is a sequence? So sequence is an ordered collection of infinite numbers, loosely speaking, say 5, 6, 7, 9. Okay, this is an example of a sequence. Okay. So sequence is a function. So now you can think about this as place one, right? This is one, this is second place, this is third place, this is fourth place. You can't interchange them. Interchanging them is not okay. It will become a different sequence. So sequence is this ordered collection of numbers. This ordered collection can be also thought of as a function from natural numbers z plus 2 r. If you're thinking about sequence of real numbers. So namely Sn, so you think about it, S1 will be denoted by S1, S2, S of 2 will be denoted by S2, so on and so forth. And we write the whole sequence as S curly bracket, all right, Sn in the curly bracket. Now, sometimes the sequence have domain can be made in a way to include 0 as well. And sometimes this is also called as natural numbers. So this is just a matter of convention. And some people include 0 in the natural numbers and some people do not. So let's try to see a few examples of sequence. So first sequence is cos of n pi, n going from 2 to infinity. So let's write down few terms of this. So first term is going to be cos of 2 pi, cos of 3 pi, then cos of 4 pi, and so on. And this can be seen as 1. Cos of 2 pi is 1. Cos of 3 pi is same as cos pi minus 1. 1 minus 1, so on and so forth. So these are the first few terms, first 4 terms of the sequence, and I've written the whole sequence here. Now note that this sequence can also be written as minus 1 to the power n. All right. So let's look at this sequence. It has 1 plus minus 1 to the power n. And let's try to graph this sequence. So let's graph this sequence. Right, we don't need the negative part, so I'll only draw this part here. So let's first write down few terms of the sequence. So S1 is going to be, you substitute 1, you get 1 minus 1 by n, right? So minus 1 by, so it's going to be 1 plus minus 1 to the power 1 by 1, which is going to be 0. Let's look at S2. S2 is going to be 1 plus 1 by 2, which is going to be 3 by 2. S3 is going to be 1 plus, now it will be 1 minus 1 by 3, which is going to be 2 by 3. What about S4? S4 is going to be 1 plus 1 by 4, which is 5 by 4. S5 is going to be 1 minus 1 by 5, which is going to be 4 by 5. So let's plot these points and see. Let's graph this sequence. So sequence only have the values at 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so let's graph at these points. So value at 1 is 0. Value at 2 is 3 by 2. So suppose if this is 1, So if this is 1, the value at 2 is going to be 3 by 2, which is bigger than 1. Value at 3 is 2 by 3, which is less than 1. So I'm going to basically draw 1 with the dotted line to keep that visible in my mind, because you see the values are kind of moving around 1. At 4, the value is 5 by 4. At 5, the value is 4 by 5. At 6, if you find out at 6, that is going to be 1 plus 1 by 6, which is going to be 7 by 6. 7 by 6. The next one will be 6 by 7. Then it will be S8 is going to be 1 plus 1 by 8, which is 7, which is 9 by 8. So 9 by 8, and then the other one will be 8 by 9. So when you look at the graph of this sequence, you can see the value is converging closer to what? The value is getting closer and closer to 1. So from here, we get the idea about the limit of the sequence. So limit of this sequence is basically as you go further and further, you will get closer and closer to 1. So let an be a sequence. This sequence has limit L. If we write, limit of n goes to infinity, an is L, or we write an goes to L as n goes to infinity. When is this the case? If we can make terms an close to L by taking n sufficiently large. So if limit of n goes to infinity an exists, we say that the sequence converges, or it is convergent sequence. Otherwise, we say sequence is divergent, or the sequence diverges. Yeah. So the more rigorous definition is epsilon n definition. So sequence an converges to L if, what happens if for given epsilon greater than 0, that means you choose how much close you want to be to L. You can always find an integer n in n such that an minus L is less than epsilon whenever n is greater than n. So you can basically decide, okay, you have this epsilon delta, epsilon n game. You say, well, I give you epsilon greater than 0. And for that epsilon, you should be able to find n such that an minus L is less than epsilon whenever n is greater than equal to. Okay. All right, so now let's see, does this sequence converges or not? Does it sequence converges or diverges? So one way to see this is the following. You want to basically see limit as n goes to infinity of 2n plus n by 3. So you want to basically see what is this limit as n goes to infinity. So one way to look at this is the following. You can basically limit as n goes to infinity of 1 by n is 0. So if you divide top and bottom by n, you will see this is going to be 1 plus 3 by n. And as n goes to infinity, this will go to 2. So this sequence indeed converges, and converges to what? 2. So therefore, we can say 2n plus n by 3 converges to 2. So you notice that you're taking the limit which you did in the case of calculus 1. So you can think about it in the following way. So consider a sequence fn equals to an. So your sequence is given by some function, and you basically put n values to get an, where n is an integer. Then if limit of x goes to infinity of f of x is L, then limit of n goes to infinity of an is also L. So this gives you the following technique of using calculus 1 for computing the limits into here. Okay. So notice the difference. The difference is that f of x could be a continuous function, whereas ans, your function, your ans are only defined for natural numbers. So they are discrete in some sense. So the idea is if this is your f of x and your f of x converges to L, your f of x is going closer to L. If you walk along the skeleton of it, you will also reach the same value which is what? Which is L. Now, what is the power of this? The power of this is that all the properties of sequence, sorry, all the property of limits in the continuous functions can be imported here. So, for example, let's look at an example in a minute. Before that, consider the following. So we say limit as n goes to infinity of a n is infinity if what happens for every positive m, there exists an integer n such that a n is greater than m whenever n is greater than n. So this means what? Your a n is getting bigger and bigger. What does it mean? It means that if you basically say any m, then after certain n, an will be all bigger than m. So you can't really set a bound on m. It will keep on increasing forever. Okay. So this is why, this is what we mean by limit as n goes to infinity of an is equal to infinity. Now there are a few more facts about sequence. So if you take two convergent sequence, you add them, you get a convergent sequence. If you subtract them, you get a convergent sequence. If you multiply them, you get a convergent sequence. So let's work on this. So if an and bn are convergent sequence, then limit as n goes to infinity of an plus or minus bn is same as limit as n goes to infinity of an plus or minus limit as n goes to infinity of bn. If you have constant times an, the constant can come out. So we have c times limit as n goes to infinity of an. In particular, this means limit as n goes to infinity of c is basically c times limit as n goes to infinity of constant sequence 1, which will be c. Same thing works for the product as well. For quotient, it is different because this limit an divided by limit of bn, so limit n goes to infinity of an divided by bn is equal to limit as n goes to infinity of an divided by limit as n goes to infinity of bn, as long as the denominator does not goes to 0. Yeah, if it goes to 0, then we have to deal it in a different way. So same thing about the powers as well. Limit as n goes to infinity of an to the power p. The limit can be brought inside the power only if p is greater than 0 and an is greater than 0. Otherwise, you have problems of what? Square root of negative numbers and so on. Another is limit as n goes to infinity of absolute value of an is 0, then n goes to infinity of an is also 0. Now, suppose you have three sequences an, cn, and bn, such that an is less than equal to cn, less than equal to bn. If the limit of this guy and limit of this guy are both L, then limit of n goes to infinity of cn is also L. This is kind of like a squeeze theorem for sequences, right? The limit of cn is getting squeezed in between limit of an and limit of bn. The last one is the following. Limit of n goes to infinity of an is L. And if you have a continuous function at L, then the limit as n goes to infinity of f of an is same as f of L. So this is another interesting one. Helps you to compute the limit. All right. So these are the laws of limits for sequences. Let's see how is that going to help us. Now, show that this limit converges to 1. Sorry, this sequence converges to 1. So we are interested in limit as n goes to infinity of n by, so nth root of n. So what we'll do is the following. This is going to be same as limit as x goes to infinity of x to the power 1 over x, right? Because nth root of n is same as n to the power 1 by n. Now as x goes to infinity, this is of form what? Infinity to the power 0, an indeterminate form. So therefore we can apply L'Hopital's rule. So let L be equal to limit as x goes to infinity of x to the power 1 over x. So I'm calling this limit to be L. Then take ln on both sides. So we get ln L equals to ln of limit as x goes to infinity of x to the power 1 over x. Now limit and ln commute, because as x goes to infinity, x is positive and ln is positive there. So this will be limit as x goes to infinity ln of x to the power 1 over x. This is going to be limit as x goes to infinity ln x over x, which is going to be by L'Hopital rule. So L'Hopital's rule. Note that this is again of form infinity or infinity, so we can apply L'Hopital's rule. So by L'Hopital's rule, we get limit as x goes to infinity. Derivative of top is 1 over x, derivative of bottom is 1. And as x goes to infinity, this goes to 0. So therefore, we get ln L is 0. This means L equals to 1. And which is what we wanted to prove, that it converges to 1. So an is sine of n pi by 2. And now if you see limit as n goes to infinity of this, so we get the following. If you look at the terms here, you will see that sine of 0 is what? Sine of, so when n is 0, you get 0. When n is 1, you get 1. When n is 2, you get 0. When n is 3, you get minus 1. And this pattern repeats forever. Yeah. So this is going to be, if you look at this is same as 0 if n is even. Okay. And if n is odd, it's two different kinds of odd. All right. And is, so what happens when it's odd? It depends on when it's form, n is a form of 4k plus 1, and or n is a form 4k plus 3. When it's of form 4k plus 1, you will see the answer is 1. When it's of form 4k plus 3, it is of the form, what? It's a minus 1. So it doesn't reaches, so it doesn't gets close to any fixed real number, right? It's oscillating all over. Therefore, we say an is divergent. Now, next question. Does this sequence converges or diverges? And for what value of r does this sequence converges? Can you basically look at it, please? So notice that cos values are between, so cos n pi, the values are between minus 1 and 1. So if you divide by n throughout, so cos, so dividing by n will give us what? So this gives us 1 by n is less than equal to cos of n pi divided by n less than equal to 1 by n. Right. Now, why did the inequality did not change? Because n is positive, right? Now note that limit as n goes to infinity of 1 by n is equal to 0, which is same as limit as n goes to infinity of minus 1 by n. Therefore, by squeeze theorem or sandwich theorem, whatever you want to call it. So squeeze theorem, it's also called sandwich theorem, by the way. By squeeze theorem, limit as n goes to infinity of cos of n pi over n is equal to 0. So B, there are many ways to look at B. One way to look at B is the following, that limit as n goes to infinity of 1 by a to the n is 0 if a is greater than 1, right? So we have limit as n goes to infinity. So if your r is 1 by n, a, so if a is less than 1, so here's the story. If r is less than 1, then what do we get? We get r equals to 1 by, or r can be written as 1 by a, where a is greater than 1, right? So if your r is greater than, so let's deal with this case first. Okay. So in this case, we have limit as n goes to infinity of r to the power n is same as limit as n goes to infinity of 1 by a to the power n, which is going to be 0. So when r is between 0 and 1, you get this. Similarly, if r equals to 0, you can see that limit as n goes to infinity of r to the power n is constant 0 sequence. So that is going to be 0 as well. Now consider, so from here, consider the following. Consider absolute value of r is less than 1. For such r, and r is not 0. Let's consider this case. So in this case, you can see that again, r can be written as, absolute value of r can be written as 1 by a. So in this case, we have absolute value of r equals to 1 by a, where a is greater than 1. So limit as n goes to infinity of absolute value of r to the n is same as limit as n goes to infinity of 1 by a to the power n, 1 by a to the power n, and that is going to be 0. So if absolute value of r is less than 1, then what do we get? We get limit as n goes to infinity of r to the n is equal to 0. Yeah. But r to the n is same as, this implies limit as n goes to infinity of absolute value of r to the power n is 0, right? Because these two are same things. And now note the one of the laws of limits you have seen. If limit of absolute value is 0, then the limit is 0. So in this case, we see that since limit of absolute value is 0, this implies limit of n goes to infinity of r to the n is equal to 0. This is if absolute value of r is less than 1. Now, if r is equal to 1, then limit as n goes to infinity of r to the n is 1. So it also converges. If absolute value of r is equal to -1, then limit as n goes to infinity of -1 to the power n oscillates and diverges. Yeah, oscillates between -1 and 1. Now, what is the next case? Limit as x goes to, if r absolute value of r, limit as, what about the other cases? Limit r to the power n as r goes to, so as r and n goes to infinity is infinity if r is greater than 1. Similarly, limit as n goes to n goes to infinity of r to the n oscillates if absolute value of r is less than equal to, sorry, if r is what? R is less than equal to -1. So therefore, what do we get? It only converges when, so when does it converges? When R is greater than -1, less than equal to 1. We'll see later why that is useful. Now, sometimes it's hard to find out the limit of a sequence, but we can basically see in some other ways whether the sequence converges or not. So for that, let's develop the following machinery. So we call a sequence an to be increasing if an is less than an plus 1. That means what? If this is your an plus 1 is going to be bigger. Then the next one will be bigger, and so on and so forth. So such a sequence is called increasing sequence. So similarly, we can define the decreasing sequence. What happens in decreasing? An is greater than an plus 1. That means the next term of the sequence is smaller than the previous term. We call a sequence monotonic if it is either increasing or decreasing. It has only one behavior. Either it is increasing or either it's decreasing. So such sequences are called monotonic. So let's decide which of these are increasing, decreasing, or neither. So let's work with the first one. So what do we have? So here in this case, let's see what is an. So an in this case is a. You can see that an is decreasing, right? Why is an decreasing? Notice the following. So an is made out of, an is 1 plus 1 by n. Notice that 1 upon n, notice that n plus 1 is bigger than n, right? So this implies 1 by n is greater than 1 upon n plus 1. Now, if you add positive on both sides, you'll see that this is going to be bigger than 1 plus 1 upon. This is your an. This is your an plus 1. So you see that an is greater than an for all n, right? I did not take any specific value for n. So this is increasing. So therefore, an is increasing. Let's look at part B. Bn, so let's see. So Bn similarly is monotonically decreasing. Why is it decreasing? Yeah. Sorry, my bad. That means what? An is decreasing. That is correct. Right? Because an is bigger than n plus 1. That means the next terms are getting smaller and smaller, so it's decreasing. So let's look at Bn. We want to look at Bn. So Bn can be worked out in the same way. Notice that from here we get 1 by n is bigger than 1 upon n plus 1. Now if you put a minus sign on both sides, you'll get minus 1 by n is less than minus 1 upon n plus 1. This implies adding 1 on both sides will give us. So this is your an. So an, oh sorry, bn, we are calling the sequence bn. So bn is less than bn plus 1 for all n greater than or equal to 1. Therefore, bn is decreasing. Sorry, bn is increasing, my bad. Bn is increasing sequence. Now, what about Cn? Let's look at Cn. So let's look at first term of Cn. So first term of Cn is 1 minus 1 by 1. So 1 minus 1, which is 0. We have already found out these elements, right? So C2 is going to be 3 by 2. C3 is going to be 2 by 3. C4 is going to be is 1 minus, so 1 plus 1 by 4, which is 5 by 4. C5 is 4 by 5. So clearly you can see that C1 is less than C2 but C2 is what? Not less than C3. So this means what? It is not increasing or decreasing. Yeah. So why? Because there are some terms where the next one is bigger than it, but there are some terms where the next one is smaller than this, right? We have this. So therefore, what? C is neither. So this is neither increasing nor decreasing. Now, why did we discuss this? The reason for that is the following. If you take a sequence which is bounded above, that means what does it mean by a sequence which is bounded above? That means you take a sequence. If it is there is an m such that all the terms of sequence is less than equal to m, then we say sequence is bounded above. Similarly, when do we say sequence is bounded below? When we can find m such that all the elements of sequence, so suppose few elements of the sequence are here, all the elements of sequence are bounded below by m. That means what? All the elements of sequence are greater than equal to m. So we say if the sequence is bounded above and below both, then we call such a sequence as bounded sequence. Yeah? That means the values of your sequence are between some small m and capital M. They are bounded between these values. So here's a monotone sequence which tells you the following. Every bounded monotone sequence is convergent. So what does it mean? It means if you take a sequence which is bounded and it's also monotone, monotone means it's either increasing or it's always decreasing. It says that every bounded monotone sequence is convergent. It's kind of clear from the picture because if you take a sequence which is increasing and it's bounded above by m, then at some point it has to start getting closer to, right? Otherwise, it will basically overshoot m. So this is called the bounded sequence theorem. Now, investigate the following sequence, which is defined recursively. What do you mean by investigate? You have to find out whether it converges or not. So let's embark on this problem. So let's compute first few terms of this, okay? Just to get a feeling of what is happening, all right? So what is your A1? A1 is square root of 6, which is roughly 2.449. Let's get, what about A2? A2 is 6 plus A2, which is clearly now you're looking at bigger than, so this is going to be 6 plus square root of 6. So clearly this is going to be bigger, which is roughly 2.906. Similarly, A3 is going to be roughly 2.9844 and so on. So it looks like, yeah, limit seems to be 3, right? So now we will basically show that this sequence is increasing. So claim, so you can see that there's an increasing pattern, right? So claim AN is increasing. Yeah. So how do you prove this? How do you basically prove such a thing? Well, one way is basically, so that means what? That is what we want to show, that AN plus 1 is greater than AN for all n belonging to Z plus. So we'll prove it by mathematical induction. So how would we go about mathematical induction? So first of all, base case. Base case, say A1 is root 6, and that is clearly less than what? 6 plus root 6, right? So you're adding something positive, A2. So it is true. So this is the star. Star is true. Is star is true for n equals to 1. Now, assume, so induction step. So induction step, we get what? Suppose. So induction step, you suppose. So suppose AK plus 1 is bigger than AK for some K in Z plus. Then we want to prove now, to prove for K plus 1. So what do you want to do? We want to prove this for AK plus 2, right? K plus 1 plus 1. So AK plus 2 is going to be square root of 6 plus what? AK plus 1. Now 6 plus AK plus 1 is bigger than 6 plus AK. Why is that? Because AK plus 1 is bigger than AK. Now this is going to be your AK plus 1, right? So therefore, this is true for K plus 1, and by induction hypothesis, so sorry, so this is true. So this is true. This means star is true for K plus 1. Therefore, by principle of mathematical induction, the principle of mathematical induction, we have what? We have AK or AN plus 1 is greater than AN for all n in n, or all, for all n belonging to Z plus. That is, we want to show that actually AN is between these values for all n in C plus. So let's see, why is that the case? Again, we can use a induction again. We can use induction. So how would we use induction? So induction step. So clearly AN is greater than A1, right? For all n, because it's an increasing sequence, right? So therefore, clearly square root of 6 is less than equal to n for all n. That part is not that difficult. Yeah, straightforward. What is interesting is the other part, that claim that an is less than equal to 3. Sorry, an is less than equal to 3. So claim an is less than equal to 3. So we'll basically use the following. So an is less than equal to 3. So how do we prove it? Base case. We'll use induction. Use induction. Again. So base case, a1 equals to root 6, that is less than equal to 3. So base case is true. Now, hypothesis, induction hypothesis. Induction hypothesis assume that AK is less than equal to 3 for some K. B plus. Now we want to prove for K plus 1. So now we want to prove that this is true for K plus 1, right? So what is my AK plus 1? my ak plus 1 is less than equal to square root of 6 plus ak, which is less than equal to, now ak is less than equal to what? Ak is less than equal to 3, so we have 6 plus 3, which is going to be square root of 3, which is 9. So ak is less than equal to 3. Therefore, by mathematical induction, an is bounded. Yeah, bounded by what? Bounded by above by 3 and below by square root of 6. So not only that, in this case we can find, so by monotone so we know that by monotone convergence theorem, this theorem here, by monotone sequence theorem, so by monotone sequence theorem, we have that, what do we have? We have an converges, because it's bounded since it is monotone and bounded. Okay, so bounded monotone sequence is convergent. That is what the monotone sequence theorem is. Now, can we go further and find the limits? So let's find the limits. Okay, so that means that is a, which is limit as n goes to infinity of an exist. Now we have an plus 1 equals to 6 plus an. Take limit on both sides. So limit as n goes to infinity of an plus 1 is equal to limit as n goes to infinity of square root of 6 plus an, which is limit as square root of limit as n goes to infinity of 6 plus an. And now if you write it down, this is going to be, we get this limit is going to be a, and we get a equals to, and this limit is going to be square root of 6 plus a. So squaring on both sides, what do we get? We get a square equals to 6 plus a, which means a square minus a minus 6 equals to 0, which gives me a minus 3, right? You get a minus 3 times a plus 2 equals to 0. This means a equals to 3 or a equals to negative 2. Now note that your sequence is bounded between, now since we have, since AIs belong to what? They are between, since AIs are between root 6 and 3, we have a equals to 3.